goes from this whole mess just to that. Just to the assumption of P. Right? We took a P, which was just an assumption to begin with, put it together, took it out. If we had never bothered doing that, we would have just had our assumption. So when we reduce, what we end up with is just the assumption. Let's take a look at a kind of schematic form to give you an idea of how this works more generally, right? So the basic idea of reduction, and this will be true of all our reductions, is we're going to take our reduction candidate proof, right? Our proof that introduces a connective and then immediately eliminates it. We're going to take that candidate proof and we're going to kind of mine it for parts, rearrange those parts in a certain way. That's the idea. So whenever we've got, so let's look at the general form and then we'll look at another example that's a little bit more involved. So think about a conjunction. So suppose you have a piece like this in the middle of your proof, right? You've got some proof of A, it came from somewhere, I don't know where. You've got some proof of B, it came from somewhere, I don't know where. Suppose you introduce a conjunction and then immediately eliminate it, say on the left. Right? What we want to do is take, and then after you eliminate it, you go on and do something else, maybe. I don't know what. We want a general way, whenever something like this happens in the middle of a proof, we want a general way that we can mine that proof for parts and put those parts back together so that this never happens, right? So that this conjunction never gets introduced at all, right? Because it was introduced and then eliminated, so we may as well never bother with it. How could we mine that for parts and put those parts back together so that we skip over that middle step? That's right, you could not. Right, so the elimination rule here, you can only eliminate something if it's actually there. So you definitely can't just start from up here and apply an elimination rule. Or at least not apply this elimination rule, right? If A is itself a conjunction, well then maybe you could eliminate that conjunction, but you can't count on that in general. So that's definitely right. So we start with two different proofs. One's a proof of A and one's a proof of B. We put them together using conjunction introduction, then we extend that result with a conjunction elimination to get ourselves a proof of A, and then we go on to prove something from A. You know, I don't know what. Right? So what we want out of this whole mess here is some proof or other of A so that we can go on and do something with it. Right? That's what's below this. You can think of this as like a needless detour that we're cutting out. Right? So what's past the needless detour, what's below the needless detour, we need to start from a proof of A to do whatever it is. And before the needless detour, we have two things. We have a proof of A and we have a proof of B. How can we avoid the needless detour? Yeah, right, we started with two things, proof of A and a proof of B. We need a proof of A. Oh, we have a proof of A. So we could just forget about the proof of B entirely. That's it exactly, right? We don't need to do any elimination rule because we can't do any elimination rule. We just forget about it. And we say, okay, that proof of A that we started with, whatever it was, let's just use that. Right? We took this needless detour all to get around to a proof of A, but we started with a proof of A. So let's just use that proof of A. So in other words, whenever you have something like this, and let's say, I don't know, let's say this proof is a big triangle, and this proof is a big wobbly bit, and this proof is a big rectangle. Right? Those are the pieces that we're going to now take apart and rearrange. The resulting thing is going to take a proof of A. And what proof of A? Well, the proof of A that we started with. Right? Whatever that triangle proof was. And it's going to use it how? Well, however that rectangle was, right? Whatever we were going to go on and do with it. And the whole spiky wobbly proof of B, we just throw away. Never used it, right? We put two things in a box, we took one of them out, and then forgot about the box and the other thing in it. Well, just skip around that. Right? So this is how conjunction reduction works in general. Whenever you have a conjunction that's introduced and then immediately eliminated, it'll look like that, or it'll be the right elimination rule rather than the left elimination rule, right? There's two possibilities here for left and right elimination rule. And the idea is, well, you just take what you need and then repeat. So let's take a look at an example. And let's take a look at a cruel example. Because sometimes that's fun. P and P and P. And let's introduce P and P to P and P. Conjunction introduction. P and P and P and P and P. And conjunction elimination on the left, so P and P and P, and elimination on the left to P and P, and conjunction elimination on the left to P. Okay. First question, is that a proof? That is, did I screw up in writing that down? Two things together to one, that looks good. Two things together to one, that looks good. Two things together to one, that looks good. And all these are labeled with conjunction introduction. Now eliminate on the left, and it is the left conjunction. Eliminate on the left. Okay, looks good. So there's a proof. Is this proof possible to reduce? Totally. Where? It's not quite at the very top. So up here, right, it's all of this is introductions. But we need to be able to, we need to introduce something and then immediately eliminate it. So someone say third line. Like this giant mess, like 1, 2, 3, yeah, this is the one, right? Because this has been introduced and then immediately eliminated. And it's that IE. Right, wham, wham, IE on the same connective. That's the sign of a reduction. So let me get a new sheet of paper here. So let's think about what that should reduce to. First thing we want to look at, right, again, think about our schematic approach here. We say, okay, we've got this triangle proof of P and P and P. We've got this wobbly proof of P and P. Now we're going to introduce the conjunction, immediately eliminate it, and then we're going to take that and have a rectangle continuing on from it. So we want to take those pieces, rearrange them in the way that we've been instructed to do over on the left, right, in a way that says, going to take this thing, which is a proof of P and P and P, and continue it this way, which continues from a proof of P and P and P, cutting out the middle. Right, so the result in this case, right, we start from our triangle proof, P and P, P, conjunction introduction, P and P and P. That's our triangle. And now we take the rectangle, which wants some input like that, and continue on. Conjunction elimination on the left gives us P and P, and then conjunction elimination on the left gives us P. So this whole, overlap it that way. So this whole upper proof, which is a perfectly good and lovely proof, it's a wonderful proof, it's great, it's got many virtues, there's nothing wrong with this proof. But what it is a candidate for reduction, right? It's ready to turn into a different proof. And the proof it turns into is this lower one, which is also a perfectly good and lovely proof. It's no better or worse. It's the result of reduction from the first one. What about this second proof? Is this a candidate for reduction? I see both yeses and nos around the room, which is always a good sign. The answer is yes. This one is definitely ready for reduction because we once again have something that's introduced and then immediately eliminated. Right? What's happened, we cut out a detour, but we found as a result of that cutting out that where we plugged in is itself still a detour. Right? And that detour can be cut out in the same way. So we start from a proof of PNP here. We move on from a proof of PNP here, right? We've got conjunction introduction and then immediately eliminated on the left. So this itself reduces yet again, and it reduces just to that. Right? We've taken our original assumption of PNP, it lives there, and we've moved on from it in the way we intended to move on from that proof of PNP. So that's worked again. Now, what about this proof? Is this proof a candidate for reduction? No. That's it. Nothing's introduced and then immediately eliminated. Right? Something's been assumed and then had an elimination rule apply to it. But assumption is not introduction. So nothing there has been introduced and then immediately eliminated, so there's no more reducing to do. We're done with reduction there. And we'll find in the system that we're looking at, or in all the systems that we look at this semester, reduction always works like that. It always comes to an end. In the main systems we're looking at anyway. Some of the big exercises might not be so well behaved. But in the main kind of core systems that we're looking at, you might be able to take multiple steps of reduction, but you'll always reach a point where you can't reduce anymore. Right, so all these proofs are good. They don't become better proofs. For now, they become shorter proofs, although, as I said, later on, reduction might make things bigger. But what reduction does is it just takes a proof, some proofs, and transforms it into a new kind of proof, when it's possible to do so, right? Not all proofs can be reduced. For example, this last one can't be. So that's our overview of conjunction for this sort of thing. What we're going to do over the next few weeks is a similar sort of pattern. For each connective that gets brought into the unit, we're going to look at introduction rules and elimination rules, which let us build more and more proofs, and reduction procedures, which transform proofs in more and more ways. So that's our plan for the next several weeks. I hope you all have an awesome one. And if you have any questions at all about the content or difficulties with anything, the best place to ask that is very much on the perusal, because that's where everyone can benefit from your questions. I think a lot of people are going to have very similar questions throughout the unit. So if you ask them there, everyone can benefit. But of course, feel free to be in touch with me as well. Have an awesome one. I hope you all stay rocking. Yeah, totally.
It's good. I was wondering, I just copied it down.
Yeah.
I was wondering how you get from, I guess I might have missed a little bit.
Yep.
In terms of like the bracketing, but if you just eliminate, first question, if you eliminate the left, is that just all of that, or just the brackets? It's basically just eliminating that.
So you've always got to look to the main connective. So here we're eliminating conjunction, but there's a lot of conjunctions up there, right? So the one we care about is always the main connective. So in this case, do you see which conjunction there is the main connective? Totally. So when we eliminate that main connective on the left, what we're left with is whatever's to its left. So you see what's to its left is that thing, and that's what comes down right below that.
So you said eliminate, but we're kind of just keeping whatever's on the left.
Yep. So we've eliminated the conjunction. We haven't eliminated the left conjunct.
Okay.
We've eliminated the conjunction, and the L means we're preserving the left conjunct. So yes, so you look to that main connective, and whatever that main connective is, it's its left conjunct that we save with conjunction elimination on the left. And on the right, it's the same, but with the right conjunct. Sweet. No worries. Have a good one, Ben.
Hi. Yeah, another good question. Kind of like where the value is, and I'm not reducing. Because if you assume P to be true and you assume P to be true, and then you remove one of your assumptions and assume P to be true.
But that doesn't say you've assumed P to be true and you've assumed